Now, we would like to look at a problem that involves a given molar solubility and trying to find out what is the Ksp. Now, the way we find the Ksp is the same as the other questions that we have done previously, which is to find out the equilibrium concentration of the products and the reactants. And then we put the concentrations into the expression and we calculate. It is the same concept. And now, what is different is that we have a term called molar solubility. So the first thing that I would like to go over is the meaning of the molar solubility. So we have a solid, and let's say we have a beaker of water. Okay. So before we put the solid into the water, there's nothing in the water. It's just water, no ions. But when we put the solid into the water, what's going to happen is that the solid, it will dissolve a little bit, and then there is a certain amount of the ions that could exist in the solution, and when it hits the maximum amount of the solute being possibly contained in the solution, it becomes a saturated solution. And when it is at a saturated solution, it is the equilibrium stage where the rate of the dissolving is the same as the rate of crystallization. So we would like to find out what is the concentration at equilibrium. What is the concentration of the ions at the equilibrium? So the molar solubility, it simply means that how much is going to be dissolved to make a saturated solution. So it is given here. That means this particular amount is going to dissolve. Okay? This amount will be dissolved in the water. So what we can do is to first start off with the ice table, because we understand that it is not at equilibrium initially. And now, since it is a solid, we would not write anything for solid because there's no concentration could be expressed in the solid. And then we can just focus on the ions or the products. Initially, there's no ions. That means it's going to be 0 molar. Okay? What is the change? Well, in here, the change is the amount of the solid being dissolved in the water, which is the molar solubility. Because when this amount of the solid is being dissolved, then we will have a saturated solution. We achieve the equilibrium, or the solution achieves equilibrium. So we would plus 1.24 times 10 to the negative 3 molar. That's for calcium ion. And now for the fluorine ion, since there's a coefficient of 2 here, it means that the change should be twice as much as this one, because of the mole ratio. So what we do is to have 2 times 1.24 times 10 to the negative 3. That many molar. So what's the equilibrium concentration? We have 1.24 times 10 to the negative 3 molar. And here we have 1.24 times 10 to the negative 3 times 2. So we have 2.48 times 10 to the negative 3 molar. Then we draw a line so that you can see it easier. So now we have the concentrations. What's the next step? Well, we would like to find the Ksp. So let's first write down the Ksp expression. Product over the reactant. Product over the reactant. But now, in this case, the reactant is a solid, so we can ignore the solid. That means the expression is going to be just the calcium ions times the fluorine ions with the exponent 2, okay, raised to the second power. And what is next? The next is that, okay, we have the expression. We need some numbers to put in here and calculate. What numbers do we put in here? It is the concentration at the equilibrium. So, meaning these two concentrations. So the concentration of calcium ion is this. So we put down 1.24 times 10 to the negative 3 molar. And then what is the concentration of fluoride at the equilibrium? This one. Just make sure you don't forget to square this number. A lot of people got this confused. It looks very weird that the coefficient is being used twice. You first multiply this by 2, so you use it once, and then you have the square, which is also the coefficient, so it looks like you use the coefficient twice. Yes, it is true, but we are using it at 2 different levels. First, it makes sense to use it here because the change has to be proportional based on the balance equation. This is why we multiply this number by 2. And then, at the very beginning of the tutorial, we said that we go over why the coefficient is going to be written as an exponent, because that's coming from the Rave's law. So it makes perfect sense to see how the 2 is being used here and here. Okay? So if you have another coefficient, that would be the same. If you let's say have a 3 here, then this number will be multiplied by 3, and then here will be raised to the 3rd power. So you put this in your calculator, you should get 7.63 times 10 to the negative 9. And just keep in mind that the Ksp value has no unit, and it usually comes up to be a very, very small number because we only use the Ksp for slightly soluble compound or solids, which tends to produce a small amount of ions. That would give you a small number for the Ksp. So you may use this as a check to see if your answer makes sense.